This is problem 33, and we have a circuit with a switch. After having been in position 1 for a long time, the switch in the circuit of figure P533 was moved to position 2 at t equals 0. Given that V0 equals 12 volts, R1 equals 30 kiloohms, R2 equals 120 kiloohms, R3 equals 60 kiloohms, and C equals 100 microfarads, determine IC of 0 minus and VC of 0 minus. So we'll start with that. And so for 0 minus, we have to look at where the switch was before time t equals 0, and it was at position 1. And so before time t equals 0, it looked like this. And if the capacitor had been charged, it would have discharged through this resistor. We don't have any way for it to have recharged, and so at t equals 0 minus, IC of 0 minus equals 0, VC of 0 minus also equals 0. Okay, so now we need to find IC at 0 and VC at 0. So we know that the voltage across a capacitor cannot change instantaneously. So VC of 0 has to still be 0. So, and that's always going to be the case. The voltage can't change instantaneously. But let's take a look at the current and see it can change instantaneously. So let's see what happens. So we are now like this at t equals 0. And when you first start, when we close the switch, the capacitor is going to act like a short circuit. So when you first close the switch, it acts like a short circuit, and then eventually it acts like an open circuit. So right here, since it's acting like a short circuit, none of the current will go through R3. So we just have this nice, simple loop here, and we know that V equals IR, and here V is 12. I is what we're looking for, so 12 volts, and R is R1, and R1 is 30 kiloohms. So now we get that IC at 0 is 12 over 30,000, which is 0.4 milliamps. So now for part C, we want IC at infinity and VC at infinity. And at infinity, the capacitor acts like a short circuit, an open circuit, and so there is no current running through it. So IC at infinity will be 0. Now we need VC at infinity. And notice that the capacitor is in parallel with R3, and so it's going to have the same voltage as R3. So to find the voltage across R3, we can use voltage division. And so our VC is going to be 12 volts times R3 over R3 plus R1. So that'll be 12 volts times R3 is 60 kiloohms over 60 kiloohms plus R1 is 30 kiloohms, and that equals 8 volts. Okay, now we want VC of t for t greater than 0. So we know, and this is important, so you learned this by solving the differential equation. We know that VC of t is going to equal VC at infinity plus VC at 0 minus VC at infinity e to the t over tau, where tau is our time constant. Okay, so I just noticed something. I was reviewing the video at the end, and then I saw that I made a big mistake right here and right here. This should have definitely been minus t over tau. Can't be t over tau because then it'd be increasing to infinity. And I'll remember the minus t later, so for the rest of this video, just pretend like that minus sign is there, and we'll all be happy. And so we have, let's find our time constant first. Alright, don't know if you heard that. That was my cats. Those were my cats in the background. So our time constant is RC. Now, from the point of view of the capacitor, R1 and R3 are in parallel. And you can see that, think of source transformation, and then it's easy to see that R1 and R3 would be in parallel. And so our resistance, we just have two resistors, so we can use product over sum, will be R1, R3 over R1 plus R3, which is 30 times 60 kiloohms over 30 plus 60 kiloohms, and that will be times our capacitance. Oh, well, we won't do that yet. So this is our R, which I don't have figured out separately, and then RC is going to be 30 times 60 over 30 plus 60. Now this was kiloohms times kiloohms. This is kiloohms plus kiloohms. So that's kiloohms squared, and that's just kiloohms. So that leaves us with a kilo. So we'll have 10 to the third. And then our capacitance is 100 microfarads. So that's times 100 times 10 to the minus 6. And when we do that, that will be 2 seconds. So our time constant is 2 seconds. So now we can plug everything into this equation to get an expression for Vc at any time t. So Vc at infinity was 8, plus Vc at 0 was 0, minus Vc at infinity was 8, e to the negative t over 2, and we can write this as 8 minus 8 e to the minus t over 2. You can factor out an 8 if you want to. 8 times 1 minus e to the minus t over 2. And that will be in volts. So that is an expression for Vc at any time t. And now we need part E. Part E is IC for t greater than 0. Let's see. Let's just leave. I'm going to erase this. Don't need that anymore. Okay, so this is part E. So we know that I equals C dV dt. And C is 100 times 10 to the minus 6. 100 is 10 to the second, so 10 to the second times 10 to the minus 6 is just 10 to the minus 4. dV dt, so that's going to be the derivative, so d dt, of our expression here for V, which was 8 times 1 minus e to the minus t over 2. So we need the derivative of this, so that will be 10 to the minus 4. And now let's just think about looking at this one here where the 8 is distributed through. When we take the derivative of 8, of course that'll be 0. When you take the derivative of negative 8 e to the negative t over 2, that'll be negative 8. And the derivative of e to the anything is e to that anything times the derivative of that anything, so it'll be times minus 1/2. So we get 10 to the minus 4. That's 4 e to, now if we wanted to, we can write e to the minus, this expression is nice because you can see the time constant, but you can also think of minus t over 2 is the same as minus t times 1/2, and 1/2 as a decimal is 0.5. So if we wanted to write it, if we wanted to write it as a decimal, it would be minus 0.5t. So t to the negative 4 times 4 e to the minus 0.5t, and that turns out to be 0.4 e to the minus 0.5t milliamps, if we change it to milliamps. And that's problem 33.